All right, for geometry today, our lesson is 1.4 subsets of lines and planes. And I tried to get better about the homework, and so I put the homework assignment on there, but then I changed my mind on what you were going to do. So let's write it on here. It is actually going to be page 21. Hopefully you're loving that there's a page number there. And we're going to do numbers 2 through 44 even, and 47 through 59 odd. Okay, but I am gonna start doing that on the top of your notes each day. So this one I just copied off before I changed the assignment. So sorry about that, but there we go. All right, so let me erase that so we can move on. Having some issues here. Okay, that's not wanting to let me dock that here. So let me move it to the other side and dock it for now. Okay, so back to the lesson, 1.4 subsets of lines and planes. All right, a subset of a line, or you need a definition here. Okay, there's a room there for us to define the word, and so that is a half line. Okay, a half line. H-A-L-F, I'm getting ahead of myself. A half line is a subset of a line. It's consisting of all the points on a given side of a point on a line. A half line AB is denoted like this. Notice, right, it's an open circle with the line. And so it says the circle above the A is the origin of the half line. Okay, so we've got the arrow there. It indicates it's not included in the half line. So you may be thinking of array. This is similar but different, so we're going to talk about that in a little bit. All right, so then we have the line separation postulate, P1.4.1. Okay, so the line separation postulate says every point on a line, so every point on a line divides the line into 3 disjoint sets. Okay, so it divides it into 1 point and 2 half lines. So every point on a line divides the line into 3 disjoint sets, 1 point and 2 half lines. So the ray, this is the next definition, is array. Array is the union of the half line and its origin. Right? It's crazy. Okay, because if we think about array, ray AB is denoted with just the line. So notice the point at the end would be included. It's not open anymore. So the half line does not include the origin, it's just the line part. The ray includes the origin and the line. It's so specific. Okay, so the origin of the ray is also called the endpoint, and it is included in the ray. We don't usually draw it, but I am drawing it there kind of as the full circle, so you realize that it's there and it is included in the ray. Okay, so this says ray AB equals ray AC because both names indicate the same set of points. Okay, so AB, right, but so it originates at A, okay, it includes A, and it says AB, but that line still continues on. So that's the same thing as calling it AC because that line still continues it on. So it's also, ray AB is also equal to ray AK. Okay, it doesn't matter because the origin is still A and it's still going the same direction. So we don't care what we name it per se, it's going to be the same. Okay. So now point P is between R and S, so we're looking at this circle or this line over there. Point P is between R and S. It's denoted as RPS. okay, because R, P is in between, and then S. So that's important how we're denoting that, okay? So if R, P, and S are collinear and RP intersects RS, hold on, I'm reading the wrong thing. Yeah, PR, sorry, pardon me. So if RP and S are collinear and ray RP, PR, goodness, intersects ray PS, it equals set P. Okay, so let's break that down a little bit. Let me erase, oh, I don't know what just happened there. Nope, 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 I want, it's not erasing, it is, okay, let's see. Oh goodness, technology is wonderful. Okay, there we go. Now I'm at where we want to be. Okay, so let's look at that again. If R, P, and S are collinear and ray PR, so PR intersects PS, all right, it equals set P, okay, because where they intersect is at point P. All right, so let's see. If point Q is not between R and S, okay, point Q over here is not between R and S because Q, R, and S are not collinear. Okay, they have to be collinear to use that word between. It seems, maybe that seems pretty self-explanatory to you, like, duh, I know that. But geometry and math in general, this textbook, this curriculum, really strives to point all of that stuff out. So, example 1, it says, show that R is not between P and S. How would we show that R is not between P and S? So we're just going to like write a sentence here. So we might say, while, we need to think about, are they collinear first of all? So yes, they are. So while R, P, and S are collinear, that's an R, I don't know what happened. While they are collinear, we could say RP. So if we look at RP, array RP, I think I get my board too close, or my book too close. So RP intersects ray RS is ray RS. Right? Those are the same. We might say that they're the same. We could say it's not set R. Okay, because the intersection is, or we could say it's equal to RS. Okay, the next notation down here that we have, it says ray PR and PS are opposite rays if and only if, if and only if P is between RS. So PR and PS. So let's look at that. So we've got PR and PS are opposite rays only if P is between. And it is. Okay, so we have to be able to say that they're between. A point is between two other points in order to be able to say that we have opposite rays. Otherwise, it's just the same ray. Okay, they're equal. All right, a segment. Okay, I left this one. You don't have to write it. A segment is 2 points and all points between them. So in this case, segment RS is denoted with a line over it, just a straight line, no arrows. Right? So if we were to look up at our same line there, we would get RS. Okay, that's our segment. So it includes P. P is in segment RS. So we would say segment RS equals set R and S, and the union, or the universal here, sorry, the universal of the set is X such that it's R, X, and S. Actually, it's to be R, P, and S. So you might need to make that change. It's R, P, and S. Okay. All right, so let's look at example 2. Let me clear our writing here and move it up so we have some room. All right, example 2. Determine whether each statement is true or false and explain. I know these are your favorite because they're definitely my favorite, except false. I really hate true and false questions. Okay, so we're using the line A, B, C, D, E up there, so line AE. And it says ray CD. So I'm going to look at ray CD here. Put my note up there. Intersection. Okay, notice that's an open circle on CA, so that's half line CA. So half line CA equals set C. So the set is C, or point. Remember, the half line is an open circle because it does not include, it's getting closed there, I'm sorry about that, it does not include the point. So this is false, okay, because half line CA does not include point C. It does not include point C. It's not, or we might say C is not an element. Oh, there we go. C is not an element of half line CA. That's another way you could put it. All right, let's look at B. Change up our colors a bit. Okay, so now we're saying ray CD union, again, it's an open circle, so union of half line CA equals line AE. Okay, so I'm going to draw line AE up here. Okay, now this is a union. So it's a little tricky because the ray includes C, the half line did not, but it's a union. We're bringing everything together, so it would now include that. The union does include it. So this one is true. Okay, it is true. Okay, and so we could think about that like C, we could say, is an element of ray CD. So how could we write that? Let's see, ray is, or C is an element of CD. So it's included, I guess we'll put. It's included in line AE. All right. And just so you know, like I do upload these on YouTube. My account is mtalbert at NCHS. So if you're struggling today and you want to rewatch it, feel free to do that. Okay. All right. Then the next one, C. All right, so we've got ray BC. So ray BC intersection ray ED. So ED goes back this way. Equals segment EB. Okay, so segment EB would be right up here. I'm going to put the endpoints on it because it's a segment and not a line. Okay, so let's think about this. So ray BC, remember this ray starts at B, is the origin, it goes all the way over there. And E, for the other one, ED, it started at E and went all the way over there. So BC intersection ED is segment EB. Remember, the intersection is what these two lines have in common. They do indeed have E to B in common. That's their area of intersection. So this is true. Okay, this is true. So we might say B, E, and all the points between them. Ooh, that's real screechy if you can hear it. I'm sorry. Are members, it says, are members of both rays. All right, one important thing to note, ray BC and ray ED extend in opposite directions, but they are not opposite rays because they don't have a common endpoint. Okay, they don't have a common endpoint. They have to have the common endpoint to be opposite rays. So back up here to our definition at the top, P ray PR and ray PS are opposite rays if and only if P is between R and S. So we're just restating that, but we're saying that's true for every single ray. It has to be between them. They can't go in opposite directions and be considered opposite. They have to have a common endpoint. All right, let's flip those notes over and look at our plane separation postulate. The plane separation postulate says every line in a plane divides the plane. I bet you can figure out the rest. All right, divides the plane into, I think maybe you might have gotten 3 disjoint sets. Oh, sets. This time it's 1 line and 2 half planes. PLANES. I'm running out of room there. It didn't. Let me write it. I apologize for that. All right, so the half plane is a subset of a plane containing all points on a given side of the line in a plane. Right? So here we've got a little note over here underneath our picture of a plane. Half planes H1, so we have H1 and H2. Oh, sorry, that was H1 is down here, I believe. No, that's H2. I'm right. Okay. H2 have a common edge, line M. So line M here has divided this plane. This is that plane separation. So the line M has divided the plane into the one line, line M, and the 2 half planes, half plane 1 and half plane 2. Okay, so the half plane edge, a half plane edge, is the line separating the plane, line M. The opposite half planes, okay, it's 2 half planes within the plane that are separated by a common edge. So half plane 1 and half plane 2 are opposite of each other because they're separated by line M. In order not to be, you would have to have multiple lines. We only have the one line in this plane, so they're both opposite half planes. All right, angle, the next note here, angle is another subset of a plane that divides the plane into 3 disjoint subsets. Okay, so we're going to look at that next and how the angle divides the plane up. So let's move those notes up. Okay, so the angle is the union of two rays with a common endpoint. So we'd have ray BC and ray BA. Okay, they're a union and their endpoint is B. So we get an angle, and we name this angle ABC. Okay, so angle ABC, it's just saying, is ray BA union ray BC. So it's the union of those two rays. All right, again, some of this is like, I know this, it's just never been put into words in this form. All right, so sides of an angle are two rays that form the angle. So we have one side is ray BA, and the other side is ray BC. Okay, the vertex of the angle is the common endpoint or the origin, that point B that was up here. I need to clear some of those notes so you can see the angle. All right, so angle notation, how we're going to name an angle. Okay, how we name the angle. So we can name it angle ABC. We use the point on one side. The vertex always goes in the middle, and the point on the other side. So we could name this angle ABC, or we could go the other way as well, because the order doesn't matter, and name it angle CBA, which is shown right here. But the vertex, the thing that matters, the vertex has to be in the middle when we name it. Another way we could name the angles is if we use a single name. We could call it angle B, or angle 1 if there was a 1 inside of it here. We call it angle 1, is used when it couldn't name more than one angle. So it could be used in this case. We'd call it angle B or angle 1 with the angle here. All right, so let's look at, the other thing we have, if you look at this diagram of it, we have the interior angle. Again, you're like, duh, is inside, and the exterior of the angle is outside of the angle. So don't overthink some of the stuff in geometry, especially when we're learning vocabulary, because they're just, they have to spell everything out. So when we get to the postulates and the theorems, and we're doing proofs, when we get to the proofs, you have all this stuff defined, and therefore you can use it. All right, example 3 says use the figure to list all other acceptable names for each angle. So angle Y, W, Z. What else could we name that? Good, we could name it, I'm going to put a comma, angle Z, W, Y. Excellent, hopefully you noticed we could also name it angle 2. Okay, it's got that 2 in there. Nothing else can interrupt, or angle 2 couldn't go for any other name. We cannot name it angle W because W also shares, it's a vertex for this other line, this other ray coming out of it. So we cannot name it angle W. Okay, let's try, nope. Let's try the next one. Okay, B there says angle 1. So what other name can we use for angle 1? Okay, so angle 1 would be this angle right here, right? Just in that space between here. So angle, good, X, WY, or angle, very nice, YWX. Perfect. So it can be either of those. But again, not angle W, because angle W shares, is a common vertex for that other ray as well. All right, next up is angle ZWX. Angle ZWX. All right, we can name it angle XWZ. And that's about it. We cannot name it angle W because it shares the W endpoint as a vertex with for too many rays, or the origin for too many rays. Hopefully you notice that these are like exact opposite, right? We're just moving the endpoints around in these names because the vertex has to stay in the middle. All right, that is it for geometry today. I hope you guys have a great day. I will see you tomorrow.